A frozen lake can look like solid ground. To a pilot in distress, it reads as a runway, flat, wide, and for a while strong enough to take the static weight of a fighter measured in tons. But that strength is rented, not owned, and it is bound to temperature and time. In the winter of 1944, a pilot from WWII committed his aircraft to this temporary surface near Pechenga in the far north of Russia. The landing held. Whether the wheels were fully down, partially collapsed, or deliberately kept up, the aluminum fuselage slid to a halt on the ice. The pilot survived and departed the area. The machine remained. Then the season changed. When the spring thaw arrived in the Murmansk region, the thermal threshold was crossed. The ice weakened and its capacity to distribute weight degraded until the support vanished. The aircraft did not crash in the traditional sense. It simply slipped from air into water, sank, and came to rest in the sediment about 28 feet below. For more than 7 decades, the war continued, ended, and faded into history, but the aircraft remained where gravity placed it. This is the recovery of a Messerschmitt Bf109 G-2, identified as factory serial 14232, through stamped markings and identification plates found on the airframe. It is a forensic investigation into a specific airframe lost on the ice smear front. The objective is not merely to pull metal from the water, it is to intercept the corrosion process and retrieve a tangible piece of engineering history. The operation is defined by the tension between the fragility of the artifact and the grip of the environment. The location is a freshwater lake, one of hundreds in the desolate landscape of the Russian north. For decades, the site was defined only by a local anomaly. Fishermen working the surface reported snags, nets returning torn or fouled by a submerged obstruction. Those accounts became the first practical data points in the search grid, suggesting a hard structure interfering with the lakebed. But a snag is not an identification. It indicates presence, not provenance. The target is a specific variant of the German fighter design. The G-2 model was introduced in 1942 as a high-performance machine built for speed and firepower. By 1944, it was an older variant, kept in service on this remote front due to supply line constraints and its reliable handling characteristics. This specific airframe carried the tactical markings of the ice smear wing, operating under the extreme weather conditions of the polar circle. Its recovery offers a rare opportunity to examine the material state of Luftwaffe equipment subjected to long-term freshwater immersion. The challenge in 1944 was survival. The challenge in 2018 is access. The lake is not deep by oceanic standards, but the shallow water column is deceptive. Visibility is near zero. The bottom is not sand or rock, but a deep layer of fine silt and organic sediment. This material acts as a preservation blanket, sealing the object away from light and current. It also acts as a visual barrier. A diver can be inches from the fuselage and see nothing but brown water. In water this dark, the investigation begins with a single question of condition. Did the airframe survive the initial impact with the bottom? Did shifting ice crush the structure as it weakened? Or did the plane settle gently and disappear into the mud? The historical record provides an entry vector, but the physical reality remains unverified until the team can turn anecdotal snags into hard coordinates and map the fuselage by feel. The stakes are technical. If the structure is intact, it is a complete museum specimen, a sealed document of 1940s engineering. If corrosion and selective alloy loss have erased critical load paths, the recovery becomes salvage. We know the aircraft went down, we know where it should be. The variable is the structural cohesion of the aluminum after 3/4 of a century underwater. Prior to any lifting equipment arriving at the site, the team must understand the environment. The lake is not a passive container, it is a chemical system that has interacted with the aluminum, steel, and magnesium of the aircraft for 7 decades. The outcome of this recovery depends on understanding the interaction between the metal and the mud. The net snags confirm the location, but they do not confirm the strength of the airframe. The recovery engineers face a distinct uncertainty. They must determine if the aircraft is strong enough to be moved or if the very act of disturbing it will cause the structure to disintegrate. Cold alone does not preserve an aircraft. Preservation is a chemistry. And in this Messerschmitt, the lake behaved like a double agent, shielding the aluminum skin from light and current while quietly dissolving the bonds that made the machine a machine. That is the duality the recovery team must plan around. The aircraft on the bottom is not the same aircraft that landed on the surface. The sequence of events that placed the airframe on the lakebed began with a thermal shift. The loss was not caused by pilot error or enemy fire, but by the failure of the operating surface. As spring temperatures rose, the ice sheet progressively lost its ability to carry the fighter's weight until it gave way and the aircraft went down. It comes to rest on the lakebed. Here, a new set of physical laws takes over. The bottom is covered in fine organic silt, and the fuselage, carrying the last of its descent momentum, settles into it and buries itself. The impact is low energy, but the effect is profound. The mud packs tight, restricts circulation, and limits how quickly oxygenated water can reach buried surfaces. In that sheltered zone, paint and markings can survive far longer than they should. But the moment the wreck is disturbed and exposed, that stability can vanish fast. However, this preservation is selective. While the aluminum skin can benefit from burial in fine silt, other components face a different threat. The German engineering design of the Bf109 used a mix of alloys for weight reduction. The bearers that mount the heavy engine to the firewall could include magnesium-rich alloys and fittings, and those materials can corrode aggressively in freshwater, especially around joints, fasteners, and mixed metal interfaces. Over decades, that selective loss can quietly erase critical load paths, even while the outer skin still looks intact. Over 74 years, while the fuselage slept in its anaerobic cocoon, the engine mounts were actively dissolving. The brackets turned to white powder and then to nothing. The engine, a massive block of steel and aluminum, lost its structural connection to the airframe. It did not move because the mud held it in place, but the bolts were no longer gripping solid metal. This creates a hidden hazard for the recovery team. The aircraft appears intact. The lines are smooth and the paint is fresh, but the skeleton is broken. If the team attempts to lift the aircraft by the tail or the wings, they expect the engine to come with it. But without the magnesium mounts, the heavy power plant is effectively a loose boulder sitting inside the nose cowling. The environment has created a paradox. It has saved the cosmetic appearance of the aircraft, preserving the history painted on its skin while quietly dismantling the structural continuity of the forward section. The silt hides this damage. It supports the engine and the fuselage in their original relative positions. To the diver or the sonar operator, the plane looks complete. But physics suggests otherwise. The recovery plan must account for a machine that is visually whole but mechanically severed. The water in the lake near Pechenga offers no visual feedback. Ambient light is extinguished by organic particulate suspended in the water column, and a diver does not truly see the aircraft until he is close enough to touch it. Therefore, the survey process cannot rely on optical cameras. It must rely on acoustics and touch. The Wings of Victory Foundation and the ICAR Search Club began the operation by deploying side-scan sonar. This technology uses sound waves to slice through the turbidity, creating a digital shadow of the lakebed. The sonar return confirmed what the local fishermen had suspected. The image revealed a hard, cruciform shape resting on the sediment. It was distinct from the surrounding geological noise. The dimensions matched the wingspan and fuselage length of a single engine fighter. The acoustic shadow suggested the aircraft was oriented nose down, with the forward section buried deep in the silt and the tail section elevated slightly above the mudline. This orientation is consistent with a center of gravity shift during the descent through the water. With the target localized, the operation shifted to physical verification. Divers descended into the freezing water to conduct a tactile survey. In the blindness of the silt, hands replaced eyes. The divers traced the leading edges of the wings and the contours of the canopy. They found stamped serial markings and identification plates on the airframe, hard proof of provenance. The digits read 14232. It was no longer a generic contact. It was a specific factory serial with a traceable wartime paper trail. The survey also revealed the condition of the cockpit. The armored windscreen was intact, but the canopy plexiglass showed signs of trauma. It was punched or shattered, indicating either a violent egress by the pilot in 1944 or subsequent damage from the environment. Crucially, the fuselage appeared structurally continuous from the tail to the firewall. However, this continuity presented a significant engineering problem. The aircraft was not merely sitting on the bottom, it was embedded in it. This introduces the critical constraint of breakout force. Underwater, weight is often secondary to adhesion. Fine silt packs around smooth surfaces, expelling water and forming a suction seal that can multiply the force required to lift an object free. In this case, the Messerschmitt was embedded up to the wing roots, in dense, clay-like mud. The winch could provide the pull, but the airframe, built for flight and maintenance, was never meant to tear itself out of a vacuum. If tension climbed while the nose and wings remained gripped, the weakened aluminum could stretch and then rip. The identity was proven and the location was marked, but the extraction plan now required one thing first: neutralize the mud's grip before any vertical lift was attempted. The geometry of the lift determines the survival of the airframe. If the angle of extraction is too steep or the tension is applied too quickly, the weakened aluminum will shear. To prevent the destruction of the fuselage, the Wings of Victory team refused to fight the mud with raw horsepower. Instead, they altered the environment surrounding the wreck, working the sediment loose with controlled water flow and hand excavation to break the seal and reduce suction. Divers descended to the lake bed with these water jets. Working by feel in the zero visibility cloud created by the excavation, they methodically cut a trench around the perimeter of the aircraft. This process was not about digging a hole, it was about breaking the seal. By injecting water between the fuselage skin and the sediment, they neutralized the suction that held the plane to the bottom. The breakout force requirement dropped from 10 tons back down to the 3-ton dry weight of the aircraft. With the friction removed, the team attached inflatable lifting bags to the wing roots and the tail section. These pneumatic devices provide a controlled ascent vector. As air was pumped into the bags, buoyancy increased, and the Messerschmitt eased up from the crater it had occupied for decades. But one reality shaped the plan from the start. The Daimler-Benz DB605 was too heavy, and its supports had been compromised by long immersion. Rather than forcing that mass to hang from an elderly airframe, the recovery was staged. The fuselage was raised and secured, and the engine was recovered separately in a second lift. This separation, while dramatic, was beneficial. It reduced the strain on the airframe during the final phase of the ascent. The fuselage broke the surface of the lake, revealing its camouflage paint to the daylight for the first time since 1944. The aircraft now floats at the surface, supported by the displacement of the lift bags. In the water, pressure is even, spread across every square inch of skin. But to complete the recovery, the machine must be dragged onto shore, and that transition, from hydrostatic support to gravity, represents the highest risk of structural collapse in the entire operation. The team must move a fragile aluminum shell up a muddy slope without tearing the belly skin or snapping the fuselage in half. This phase is governed by the risk of point loading. When an aircraft is in flight, aerodynamic forces are distributed across the wings and tail. When it is in the water, hydrostatic pressure supports the entire surface area. However, on the ground, gravity concentrates the total mass of the object onto the specific points where it touches the earth. For a crashed aircraft without landing gear, these contact points are often weak sections of aluminum sheet, not designed to carry load. If the weight is not spread out, the contact points will buckle, causing the structure to collapse inward. To mitigate this, the engineers constructed a makeshift ramp of timber logs, creating a sled path to distribute the friction. The extraction force was provided by a heavy military truck positioned at the top of the bank. A steel cable was run from the winch down to the aircraft. The decision was made to winch at the lowest possible speed. Speed creates momentum, and momentum creates shock. If the fuselage snagged on a rock or a root while moving quickly, the kinetic energy would rip the cable mount out of the airframe. By moving at a crawl, the team maintained a constant, manageable tension. The operation became a slow, deliberate slide. As the winch drum turned, the nose of the fighter breached the mudline. Water poured from the rivet lines and access panels, shedding the weight of the lake. For the first time in 74 years, the fuselage was fully exposed to the atmosphere. The visual condition of the wreck silenced any doubts about the identity of the machine. The original camouflage paint was not just present, it was vivid. The tactical number Yellow 3 was clearly visible on the side of the fuselage, a rare survivor of long submersion. In places, unit markings and stencils were still legible, preserved by the shielding effect of silt and cold water, until the air and drying began to take their toll. The fuselage was pulled clear of the water and secured on level ground. The engine, recovered separately due to the failure of the magnesium mounts, was placed alongside it. The wings were detached to facilitate transport. The Wings of Victory team had achieved the primary objective. They had retrieved the physical object. However, the successful extraction created a new, immediate threat. While submerged, the aircraft was in a state of chemical equilibrium. The oxygen-starved environment had arrested corrosion. Now, exposed to the air, the damp metal was highly vulnerable. The iron components began to flash rust within minutes. The aluminum, drying unevenly, risked exfoliation. The recovery was not the end of the process. It was merely the handover point. The aircraft was no longer a wreck site to be mapped. It was a museum artifact that required immediate stabilization. The team loaded the components onto the transport trucks. The destination was Moscow, where the final battle for the aircraft's survival would be fought not against the mud, but against the atmosphere itself. 74 years is a duration that exceeds the operational design life of a combat aircraft by a factor of 10. When the Messerschmitt Bf109 rolled off the assembly line in 1942, its expected service life was measured in months. By surviving on the lakebed for 7 decades, the airframe transitioned from a weapon of war into a historical document. The moment it broke the surface of the water, the mission changed. The objective was no longer to fight, but to testify. The wreckage was transported from the Murmansk region to the Vadim Zadorozhny Technical Museum near Moscow. There, the immediate task was the same brutal reality faced by every submerged artifact: slow the corrosion that accelerates the moment air replaces water. What follows in such cases is a choice between two philosophies. One path is full restoration, replace structure, fabricate missing parts, and rebuild the silhouette. The other is static conservation, arrest decay, document what survives, and preserve as much original material as possible. Public accounts of this aircraft focus on the recovery and initial stabilization, while the long-term scope has been discussed far less openly. The museum chose the path of conservation. The goal was to preserve the aircraft exactly as it was found, minus the active corrosion. The team disassembled the airframe not to rebuild it, but to clean it. Every rivet and panel was washed to remove the acidic silt and biological growth. The aluminum was treated with corrosion inhibitors to stabilize the surface and prevent the flash rusting that threatened the steel components. The original paint, protected for so long by the anaerobic mud, was carefully cleaned and sealed. The tactical number Yellow 2 and the camouflage pattern remain the original layers applied in the Luftwaffe paint shop, not a modern reproduction. The Daimler-Benz 605 engine, which had separated on the lakebed, required specific attention. Because the magnesium mounts had dissolved, the engine could not simply be bolted back onto the firewall without fabricating new brackets. However, the decision was made to display the engine alongside the fuselage in some configurations, or reattached with modern support structures that are clearly distinguishable from the original metal. This visual distinction is a key tenet of conservation ethics. The viewer must be able to see what is original and what is structural support. The cockpit provided the final chapter of the forensic narrative. The instruments were largely missing, removed or lost at some point between the landing and the recovery, whether through wartime salvage, later stripping, or simply the slow bookkeeping of silt and time. The canopy glass, punched and shattered, was left in its damaged state. This jagged plexiglass is not a defect, it is evidence. It marks the pilot's exit from the machine, later damage while the airframe sat exposed, or the crushing force of shifting ice. To replace it with a pristine canopy would be to lie about the history of the loss. Today, Messerschmitt Serial 14232 stands in the museum hall. It is not polished to a mirror shine. It wears the stains of the lake and the scars of its service with Jagdgeschwader 5. It does not fly, and it never will again. Its function is now educational. It allows engineers and historians to examine the actual materials and construction techniques of the 1940s, unadulterated by modern repairs. The recovery operation in the Arctic successfully bridged the gap between the loss in 1944 and the present day. The ice took the plane, the mud kept it, and the engineering team retrieved it. The file on Yellow 2 is no longer missing, it is closed.